Ground control to lunar station. Prepare your libation. We're talking integration. Our first step in talking about integration is to talk about what are called partitions. So if we have an interval from A to B, all of this, by the way, is just taking place in the real numbers. Okay, so a nice compact connected interval from A to B. A partition of that interval is a collection of finitely many points, including both endpoints, and then listed in increasing order. So the partition is just this listing of points. The first one, x sub 0, must be the left endpoint A, and the last one must be B itself. Otherwise, they just sort of march their way up. And notice these inequalities are strict. We do not repeat any values in this partition. Each interval from one point to the next is called a piece of the partition. And if you observe, the first piece goes from x0 to x1, so the second piece goes from x1 to x2, the third piece ends at x3, and so forth. So the last piece ends at xn, so n is the number of pieces that we get. The partition, strictly speaking, is the points, but we're using those points to create these intervals. It's not the hugest distinction. Now suppose you've made a partition of an interval. Okay, so you have the left endpoint, you have the right endpoint, and then some number of points in between. Delta x sub I is going to be the length of the ith piece. Then the norm of the partition is the largest length in that list. Of all the delta xi's, it's the maximum. Since we have finitely many, this is a maximum, not a supremum. Also observe that if you add up the lengths of all of the pieces, you recover the length of the interval in total. And this is just a telescoping sum. If you have x1 minus x0 plus x2 minus x1, those x1s cancel, plus x3 minus x2s, the x2s cancel, and so forth. So what you're left with at the end is just xn minus x0. xn is b, x0 is a. So a partition has a norm, and the norm is the biggest length. So in order for the norm to be small, all the pieces have to be small, yes. But if just one piece is big, then the norm of the partition is big. So the norm is the single largest piece, the length thereof. So here's a nice little picture. We've got the interval from A to B. Here it is, okay? The partition P is a list of points starting with x0, which must equal a. You have to pick the left endpoint, and you have to end with the right endpoint. Otherwise, you can just pick some points along the way, but they do have to be strictly increasing. So suppose I draw a partition like this, and I'll just go ahead and say there are 5 pieces in the partition. Then this length here is x1 minus x0. I call that delta x1. This length here, x2 minus x1, that's delta x2. So this length here is delta x3. This length here is delta x4. This length here is delta x5. And it's a little ambiguous from the picture I've drawn, but the norm of this partition would be of the 5 pieces, which length is the longest? It kind of looks like this last one is the longest. It might be the first one. It kind of depends on how I drew it, but these ones definitely look shorter. Okay, but assuming that the last one is actually the longest, it appears that the norm of this partition is that last length, the largest length. Okay, but from this picture, what we do see is, yes, if you add up delta x1 plus delta x2 and add all of these up, you take this length plus this length plus this length all the way to the end, you get exactly b minus a. And just remember, a couple of small pieces doesn't really affect the norm. If there's one big piece, the norm is big. In order for the norm to be small, you would need to have every single piece small. Okay. A refinement of a partition is when you have one partition which contains the other. Okay, so if the partition P1 has P2 as a subset, P1 is called a refinement of P2. The order of what's a subset of what can be a little tricky to keep track of. Just remember, more points in the partition would generally mean the pieces of the partition are smaller, and it's therefore called a finer partition. So if P2 is a subset of P1, which one has more points? P1 has more points. That's called the refinement. Now, it's not strictly defined in terms of how many points are in it, because you can have two partitions, one of which has many more points than the other, and neither one is a refinement of the other. This is just a handy way to keep a mental scorecard of if you do have one partition is a subset of the other, then which one is a refinement of which? The one with more points is the refinement. Now, what does immediately happen is that if you make a refinement, the norm can't get bigger. Okay, now it's crucial here that we really do have a subset here, but if I have all the same points and then some additional ones, I can't somehow magically get bigger pieces in my partition. I might get smaller ones. I may have split all the existing pieces into smaller ones, but I certainly don't magically create larger pieces if all the existing pieces are then broken down further. So refinements have smaller partitions than the things that they came from, smaller norms than the things that they came from. Another way of phrasing this isn't terribly uncommon, is to say that P2 is coarser than P1. If P1 is a refinement of P2, then P2 is said to be coarser than P1. Another thing that we're going to talk about a couple of times is what's called a common refinement. If you have two partitions that may or may not be related, okay, one might be a refinement of the other or maybe not. The common refinement is the simplest partition you can make that's a refinement of both of them, and it turns out to be the union of them. And because the union is how we create it, we use this suggestive notation of this V. The refinement of two partitions is the partition made by their union, and it's P1 V P2. Okay, so what do refinements look like? Let me erase those little corrections I made. Refinements, so if this is P2, okay, it just has x naught through xn. Now I'm going to make a new refinement, but I want it to have P2 as a subset. Okay, so P2 is going to be a subset of P1. So in order to make this new refinement P1, I definitely want all of these points, and then maybe some others. So let's throw in some points there, and that one, and maybe that one. So because it contains all of the original points, but some of the intervals have actually been broken apart into new pieces, it's called a refinement. What's the common refinement of two partitions? Well, you can see that I can clearly make two different partitions. Let's call this one P1, and then I'll switch over to a different color. Same interval though. Let's just go like this. Okay. One of these is not a subset of the other. They're just made out of different points. So neither one of these is a refinement of the other. But I can make their common refinement by taking the union. So I definitely include the endpoints. Note that the endpoints are really the only shared points between these two partitions. And then I include everything along the way by taking the union of the sets of points. So here is my common refinement of the two partitions. It is a refinement of P1 because it contains all the points of P1, but it is also a refinement of P2 because it contains all of the points of P2. So it's called the common refinement of the two. Yeah, and that's why the V is used. Why don't we just use union? You could, to be honest, since the partition was defined as a set, you could just take their union. But because we're going to be implying like slightly different intuitive ways of thinking about what these are rather than just sets, there's just this other symbol that is commonly used. So here are a couple of problems for you to work on. The main point of these problems, by the way, is to disabuse yourself of the notion that if a partition has lots of pieces, then its norm must be small. That is not true. Okay, so especially that second problem should have convinced you that it's possible to make a partition with lots and lots of pieces with a pretty big norm. Just remember, the norm is the single largest piece in the partition, regardless of how many pieces there are that are smaller than that one. Moving on, sampling points, okay, or sample points. If you have a partition, then each interval from xi minus 1 to xi, you can pick a point from it, possibly the endpoint. Note that si belongs to the closed interval, xi minus 1 to xi. If for every piece of the partition you pick one point in it, that's just called a collection of sample points. Because you are allowed to pick endpoints, it is actually possible for some points to be picked twice in this set of sample points. Okay, if you pick the right endpoint of one interval and then the left endpoint of the next, the same point will be in there twice. Now, even though we're using set notation here, if the same point shows up twice, you do need to keep track of that and list it twice. Think of it not as a set, but as a list. Okay. So again, an endpoint of an interval may or may not be chosen more than once. It might be chosen twice. But any point that's not an endpoint of an interval is chosen at most once. And of course, out of each interval, we're only choosing one point. So most points, in a very real sense, are not chosen at all. And just to back up this picture, okay, here is our interval from A to B. Let's split it up into a partition. Okay, there we go. From each interval, I'm going to pick a sample point. Let's suppose I picked this as S1, then I picked this as S2, then I pick this as S3, but now I can pick this exact endpoint as S4 because it is the right endpoint of this interval, but then I might also pick it as S5 because it's the left endpoint of this one. But I can't pick it more than twice because now I have to pick something from the next interval, and maybe I pick it here, there's S6, and maybe I'll pick the right endpoint as S7. So it's possible to pick some points more than once, but not more than twice. In a sense, we shouldn't. I mean, it kind of goes against the spirit of randomly, in a sense, picking points if you happen to pick the same point twice. Yeah, like your intuition shouldn't be thrown off by this notion. But when you come to proving stuff, you do need to remember that it is possible when picking sample points to have picked an endpoint twice. Once we've got a partition, and we've broken the interval into pieces, and we've picked sample points from all of those pieces, the Riemann sum of the function, of a function I should say, on this interval is given by the following sum. So you take each partition length, delta xi, and multiply it by f of si, which is the value of the function at that sampling point, which came from the interval of length delta xi. Add all those up, and there's your Riemann sum. Notice the inputs to the Riemann sum are the function f, the partition p, and the sampling points s. It depends on all of those. It might look familiar. You may have dealt with this back in Calc 1. You might not have, though. There's a related notion, however, that we're also going to use called upper and lower sums. So again, we've got a function. It's defined on this interval from A to B. We've got a partition. And we've made sampling points, but we're actually not going to use them. Okay, so for each interval, xi minus 1 to xi, if the function is bounded, each m sub I is going to be the infimum of the function on that interval. Each capital M sub I is going to be the supremum. Now, if the function isn't bounded, some of these might be plus or minus infinity. That's not immediately a problem. Okay, most of the time we're going to be talking about bounded functions, but these infs could be minus infinity and the sups could be plus infinity. Now, if you take the sums, instead of using the function at a sample point in the interval, you use the infimum of the function on that interval. That's called the lower sum. And instead of using sampling points from each interval, you use the supremum of the function on each interval. That's called the upper sum. And the argument here is just the function and the partition. It doesn't really depend on any sampling points anymore. But the infs and sups were over pieces of the partition, so it definitely depends on the partition. So let's take a look at what this could appear like. So here's my function from A to B. Here's my curve. Okay, I didn't draw that very well, but I never do. Here's my function f of x. Okay, I'm going to break it up just into a couple of pieces because my drawing ability is severely limited. So here is x0, x1, x2, x3, x4. My partition has 4 pieces. Now I'm going to pick some sample points. So let's pick this to be s sub 1. Here's s sub 2. Here's s sub 3. And let's pick the right endpoint as s sub 4. So this height right here is f of s1. Here's f of s2, f of s3, and f of s4, and so forth. But what about the little m's and the big M's? So little m is the infimum of the function on each interval. Now, if I'm only looking at the function from x0 to x1, it appears that the infimum is over here at the left endpoint. The supremum would be up here at this maximum. Okay, I did draw a nice continuous curve. It's got some maxes and mins. From x1 to x2, the infimum appears to be over here at this endpoint, the supremum over here at this endpoint. From x2 to x3, the infimum looks like it happens at this minimum, and the supremum maybe at the right endpoint. It's a little close based on visual inspection. From x3 to x4, the infimum is right here at the left, and the supremum is right here at the right. So I'm going to go ahead and label those in. Okay, so this right here, this is going to be M1. This right here, this is going to be M2. I'm looking at the supremums on each interval. This looks like M3, and this right endpoint looks like M4. Now, if I look for infimums on each interval, I would say here is our infimum on the first interval. Here is our infimum on the second interval. Here's our infimum on the third. And here is our infimum on the fourth. Now observe, it's possible for a sample point to exactly spit out a supremum or an infimum. It's also possible for the infimum on one interval to be the supremum on the previous one because of this endpoint overlapping business that can happen. Now, what do the different sums represent? Okay. If I were to draw a rectangle, oh, that didn't turn out very visible. Let me draw it a little nicer. If I were to draw, and I switch back to yellow, if I were to draw this rectangle, its height is f of s1 and its width is delta x1. So the area of that rectangle is f of s1 delta x1. Now if I draw this rectangle, I get f of s2 plus delta times delta x2 and so forth. But what about the upper and lower sums? Well, instead of using sampling points, if I pick minimum values, I get my lower sum. But if I were to pick maximum values, I would get my upper sums. Okay. Now, they weren't defined in terms of mins and maxes, but rather sups and infs. Because the function doesn't have to be continuous, the function f of x has had no restrictions placed on it so far. And if there isn't a maximum, there might still be a supremum, and that's why we define upper and lower sums using sups and infs and not maxes and mins. Yeah, so even if you have worked with Riemann sums before in a Calc 1 class, it's less likely you've talked about these upper and lower sums. Maybe you have, in which case that's great, but if you haven't, don't worry, we're going to spend a lot of time with them. Upper and lower sums do remove the issue of sample points. Now, sample points give a nice concrete way of looking at certain sums related to functions. You're evaluating the function at a point. You're plugging numbers in, and that's great. But it does raise this issue of if one person and another pick different methods of choosing sample points, they're going to end up with different sums, and is that okay? And upper and lower sums remove sampling points at the expense of saying the biggest possible thing would be the supremum, the smallest possible thing would be the infimum, and those might not even be in the range of the function if it's not continuous, and you have to keep track of both of them. So work on a couple of these problems. Now in the first one, we're allowing a function to be unbounded above. Just remember, on any interval where a function is unbounded above, the supremum of the function is positive infinity, and we have some rules for doing arithmetic with infinity. Okay, now the other two problems in here had to do with trying to sync up possible choices of sampling points for Riemann sums with upper and lower sums. I apologize for my bad notation. Lower sums and upper sums don't need to have the, oh, that one does need to be in there. Don't need to have the sampling points indicated, but the Riemann sums do. Okay, going on. So prove that if f is a function defined on an interval, and P is a partition, and S is a specific choice of sampling points, the lower sum is never larger than the Riemann sum, and the Riemann sum is never larger than the upper sum. And the only way for all three to be equal is if the function is constant. Okay, again, pause and work this out. This is another crucial result. Comparing upper-lower sums and Riemann sums and getting your hands dirty doing the proof yourself will be very helpful. So pause here and do it. Okay, so hopefully you went through and proved this, and on every interval, it really only boils down to the infimum of the function is less than or equal to any particular value of the function, which is less than or equal to the supremum of the function. And there it is. Now let's talk refinements. Suppose you've got a function on an interval, as we have the entire time so far. I have two different partitions, and P2 is a refinement of P1. Okay, so I took P1 and I added some points into it, and I got more intervals to make P2. The lower sum can't get smaller, so the lower sum associated to P2, a different partition, is bigger than or equal to the lower sum for the coarser partition. But the upper sums come down. Okay, so if you have refinements of partitions, lower sums get bigger and upper sums get smaller. Here's basically why. Same picture we always draw. Interval, function, nice. Now let's suppose I have a big coarse partition here. Okay. So here is how I have split the interval up, just 3 pieces. Okay. It looks like maybe this is the supremum on the first interval, and this is the infimum on the first interval. This looks like the infimum on the second, and this left endpoint is maybe the supremum on the second. Here's my infimum on the third, and it's tough to tell, but maybe this left endpoint is the supremum on the third. Now what I'm going to do is I'm going to make a refinement. So let's split this up into 2 pieces, this into 3, and let's leave this one alone. Okay, so now I have a refinement. But now if I look at how that got split up, let's just look at the left. Okay, the supremum on this interval is less than or equal to the supremum on the big thing. And on this second piece of the partition, the supremum happens to be equal to it. But I can't somehow have a piece of this interval where the supremum is bigger than the supremum was overall. And similarly, the infimum on each piece can't somehow be smaller than the infimum on this overall piece. It's even more apparent when you look at one that we've split into 3 pieces. Here's the supremum and the infimum of this interval overall. Now, if I split this into 3 pieces, my 3 supremums can't somehow be bigger than this original one, and my 3 infimums, which look like they're the right endpoints, can't somehow be smaller than the infimum overall. Now, we've actually already addressed the middle of these inequalities. This inequality right here says the lower sum of one partition is less than or equal to the upper sum of the same partition. And we already know that. The partition isn't changing. Lower sums are smaller than upper sums. Okay. The 2 exterior inequalities, this one here and this one here, are handled very similarly. That if you take a refinement, the lower sum can only get bigger and the upper sum can only get smaller. The proof is very, very similar. So we're only going to do this one, that the lower sums can only get larger. Okay. So suppose you have a piece of the partition from the original partition, P1. When I take a refinement, P2, that big piece must be a union of some pieces from the refinement. Maybe only one of them, that's okay. But there must be some collection of intervals from the new partition, the refinement, whose union makes a single piece from the original partition. And this really duplicates the picture that was up here before. If I have a single interval and I split it up in a refinement, okay, so maybe the partition keeps going this way and this way, but if I make a refinement, I have to continue to have this point and I have to have this point as well. Okay, refinements have to keep the points of the original, but now I've split it up into a certain number of pieces in the new one. And so what we'd say is that the union of this interval, this interval, this interval, and this interval makes up this interval from the original partition. Now, each of the small intervals from the new refinement is a subset of the one singular big interval from the original partition. Since we're talking about subsets, the infimum on that small piece cannot be smaller than the infimum on the one overall. This goes all the way back to results that the infimum of a subset is bigger than or equal to the infimum of the set that contains it. That's really all we're relying on here. So the infimum of a function on a small interval is bigger than or equal to the infimum of a function on an interval containing that one. Okay, so that gives us that our new infimums are bigger than or equal to the old infimum chosen every time. That this little infimum on one small piece is bigger than or equal to the infimum overall. And this infimum on one small piece is bigger than or equal to this infimum from the overall piece. Because what are we doing? We're taking the interval from xi to xi minus 1 and just breaking it up into these pieces. But the same overall infimum multiplied to each piece of this partition is less than or equal to the new infimums on each piece. And what do we have now? That this sum, the lower sum of the refinement, but only on the pieces that make up the big interval xi minus 1 to xi, is bigger than or equal to the one piece of the lower sum that we would have gotten here. So again, just to sort of try to drive this home, here is one piece of the original partition. Okay, and the function has an infimum right here. I'll call that m. Now if I split this into three pieces, so I'll call this y1, y2, y3, y4. Okay, I have made a refinement by splitting this into a bunch of pieces. It's going to have various infima on other pieces. But since little m1 is bigger than or equal to the global m, and little m2 is bigger than or equal to the global m, and little m3 is bigger than or equal to the global m, if I do m1 delta y2, I guess, because I ended this index with 2, plus little m2 delta y3, I know my indices are off, I'm sorry, but I'm just making the lower sum corresponding to these specific three pieces. But each one of these is bigger than or equal to if I had just used m. And if I add up all of these lengths, we just get the delta x from here. So if I collect the intervals from the refinement and group them according to which intervals of the coarser partition they make up, and I add up accordingly, I get that the lower sum for the refinement must be bigger than or equal to the lower sum for the original. And that's exactly what we had set out to prove. So what we're going to do later on to great effect is this is exactly right. If I make a refinement of a partition, and then I make another refinement and so forth, the lower sums are getting pushed up and the upper sums are getting pushed down, but they can never cross one another because lower sums for a particular partition are never larger than upper sums. So they are going to get squeezed closer and closer together. And maybe there will be a limit, maybe not. Now here's a very important relationship between this notion of upper and lower sums and Riemann sums. If f is a function, and let's just suppose it's bounded above, and we have a partition, then for any positive epsilon, it is possible to choose sample points so that the upper sum and the Riemann sum are very, very close. Now the upper sum is bigger than or equal to the Riemann sum. So this difference here is positive, but I can make it less than epsilon by choosing sample points appropriately. Now all of the capital MIs, the supremums on various intervals, are real numbers because we did assume f was bounded above. On each piece of the partition, if I subtract from capital MI epsilon over b minus a times delta xi, this is capital MI minus a small positive amount, but it's still smaller than capital MI. Now capital MI was the supremum of the function on that interval. So if I have a number less than the supremum, it's not an upper bound. In other words, it's possible to pick a sample point that evaluates to be larger than capital MI minus epsilon over b minus a times delta xi. I'm sorry, there's a typo there. There should be a delta xi down here. Okay. So what's going on here? if I have one piece of the partition, and here is my supremum, mi. So epsilon was a fixed positive number, b minus a is some fixed amount, okay, and delta xi is some fixed amount. So if I take mi and I take away this will definitely be smaller than capital Mi, meaning this is not an upper bound. So I can find and this little, let me draw a different horizontal line here. This is slightly smaller than Mi. So this is capital Mi minus epsilon over b minus a delta xi. Since that's not an upper bound, I can pick a sample point that evaluates to be larger than that. So for this particular method of choosing sample points, you have to do this for every piece of the partition. Okay. If I take the upper sum and I take away the Riemann sum, the upper sum always uses capital Mi, but each piece of the Riemann sum, each sample point was chosen so that this was bigger than this right here, okay, with the delta xi down there. And since I'm taking it away, I can now say this is less than. Now, when you collect all of these terms, this should be delta xi as well, I apologize. Okay, this epsilon over b minus a is now a constant that can be factored out. So I can say this is epsilon over b minus a, and now I have the sum of the delta xi's. And what's the sum of the lengths of all the pieces? Exactly b minus a. Then the b minus a's cancel, and we have this distance being less than epsilon. It's not the trickiest proof conceptually. It's just saying, if I want to force the Riemann sums to be very, very close to the upper sums, since the upper sums are achieved with supremums, just pick your sample points to be really, really close to the supremum of the value of the function. Choose your sample points so that the function evaluates to be exceptionally close to the supremums, and then you'll get that the Riemann sum is exceptionally close to the upper sum. So we can make Riemann sums arbitrarily close to upper sums, yes. And if you just repeat this argument using infimums, you can choose sample points so that the value of the function is exceptionally close to the infimum of the value of the function on each piece of the partition. And that will give you that your Riemann sum is really close to your lower sum for a different choice of sample points, okay? Presumably you have to choose different sample points to get close to the sup versus close to the inf, but it's possible to do either way. So the notion of Riemann sums is not really that different from upper and lower sums, okay? Riemann sums can be close to upper sums, Riemann sums can be close to lower sums, but it's always trapped in between the two. So in a sense, upper and lower sums are giving you like the biggest and smallest value that a Riemann sum could ever possibly be, although one of our earlier practice problems did show it might be impossible to have a Riemann sum equal an upper sum, but it will be an actual supremum of the values. Yes, what you can show, and it's not actually assigned as a problem, is that over all possible choices of sample points, the supremum of all the Riemann sums you could possibly get is the upper sum, and the infimum of all Riemann sums you could possibly get is the lower sum. This is for the partition staying the same, but being allowed to choose your sample points. Okay, here's a problem to work on. It's really very similar to the last one, just show that you can get Riemann sums to be close to your lower sums. Try to basically duplicate the previous argument, but with some inequalities reversed. As always, if you're finding these videos helpful, it's nice to leave a comment to let me know. If there's certain issues that you have questions about, you want clarified, leave a comment for those as well. Okay, so hopefully we were able to show that Riemann sums are close to lower sums if you choose the sample points appropriately. So, continuing on with establishing some squeezing type inequalities. We've got a function f, it's bounded both above and below. The supremum and infimum on the entire interval from a to b I'm calling capital M and little m. The claim is that no matter what partition you pick and no matter what sample points you pick, you have this chain of inequalities. Now observe, if you have a partition and sample point, we've already proved this entire trio of things in the middle. So all that remains to prove is this one on the far left and this one on the far right. We're only going to do the one on the left, the right is very similar. And it's actually a very, very short proof. Okay, wonderfully short. Pick a partition that's just the endpoints. Okay, well then, the infimum of the function overall times the length of the interval is exactly the lower sum for that partition. And if I use the supremum, I would get the upper sum because my partition has one piece in it. Now, any partition that you could construct has to contain A and B in it. Remember, it's part of our definition of a partition. You have to contain the left endpoint and you have to contain the right endpoint. So any partition at all that we could construct will definitely be a refinement of this really silly partition that only has the left and right endpoints. And if I'm a refinement, my upper sum can only go down and my lower sum can only go up, and that's exactly what we were trying to show. Okay, now the picture is not substantively different from anything we've drawn before. It's just instead of looking at one piece of a partition, now imagine that's the entire interval. So here's my function. So here is m. Here is little m. Now if I make any partition at all, it has to have those as endpoints. Now if I make my supremums, I will be still not larger than if I had just used capital M times B minus A. And if I were to use the infimums on each piece, I would not be smaller than if I had just done little m times b minus a. Basically, this is saying, no matter what function you do and no matter how you split it up, if you make the associated Riemann sum and interpret it as this sort of sum of rectangles, it won't be bigger than just making one rectangle with the global supremum, and it won't be smaller than just making one rectangle with the global infimum. This is really not a terribly deep result, but it will be handy later on. So why do we bother with such a simple observation? You'll see. Yeah, that's true. Upper and lower sums can't go off to plus or minus infinity, assuming we have a bounded function. That was part of the assumptions here. Because no matter what partition you pick, the upper sum cannot be bigger than capital M times B minus A, which is a fixed constant. So by choosing the partition in a really weird way, your upper sum is not going to somehow explode to infinity as long as your function is bounded above. And similarly with the function bounded below, the lower sum won't dart off to minus infinity by choosing a weird partition. Well, that's going to be it for here. All we've done is introduce partitions, sample points, upper, lower sums. We're going to continue working with them and develop our theory of integration in the next videos. So come on back and we'll see you then.